I mean, I am a little sad that you don't have the Navi look anymore, but the cat's kind of cute.
Wait, the Navi looks?
Yeah, you had like a fairy with like a hand pointing to a piece of grass. It always reminded me of Ocarina of Time.
Wait, was there a fairy in that picture?
It looked like it.
I'm pretty sure. Wait, hold up.
Now you're gonna go back and look.
Yeah. I think. Wait, do I still have it? Oh, maybe I don't have it anymore.
Oh no.
Ooh.
Oh, that's so sad.
Ooh.
That's so sad.
That's a bummer.
Time for a pop quiz.
I think the fairy was not a fairy. I think it was like a finger, like a hand. Because that was during the April Fool last year. This core April Fool joke was that they make a touching grass simulator. And,
Oh.
and if you play like for 10 minutes, they will like give you this random border.
Oh,
But I
that
guess
makes
it took it away, so it's pretty sad.
Yeah, it looked like there was like a little fairy in the background, so it always reminded me of Ocarina of Time.
Oh yeah,
Going to cut that
that's
grass, and now
yeah, that would have
like,
been so
hey,
good.
listen, hey, listen.
Anyways,
So how have you guys been doing? I
huh?
heard you
Pretty good.
are you invigilating exams right now, Sasha?
Oh yeah, I did it with one exam, and yeah.
Do you mark the exams as well, or just help with the invigilation?
Yes, I do all the boring stuff.
Oh.
Yeah, I'm split between like two instructor for my TO work this semester, and one I'm also doing a tutorial session, which is I mean that's usually more fun because you can like talk with people and do stuff.
Right, right.
But for the other guy, I'm only doing the grading and I'm also invigilate the exam. So
That is boring stuff, yeah.
yeah, that's the yeah, I agree. That's not the best part.
What about you, Slim? What have you been up to lately?
Not much. I don't have to proctor exams or grade or do anything like that. I've been preparing for the reading group on the philosophy of mathematics with Don. It will happen next week. Don is also pretty excited. So I've been reading the book on the philosophy of math and thinking of what kind of streams I want to do. I want to just read a book and do it like every day for a month and see how much I can advance reading the book over a stream, like a couple of hours a day, and preparing the next video for the YouTube channel, but just the usual. What about you? What have you been up to?
Yeah, I have seen. Oh, Jeff is saying my mic might be a little. Let me pop that up for you a little bit. I have seen some of the videos coming out, which is pretty awesome. So congratulations on getting things going over on the YouTube side. I've just been freaking busy. Like it's exam time. It's like curriculum planning time for me as the department chair. So I've these past 2 weeks have just been like bombardment of meetings trying to figure out what we're doing for the next like couple academic years. Our government has put out a crazy like proposal that's shifting a lot of the colleges into a more applied kind of format. So a lot of the meetings have been just trying to figure out what's our baseline, what does our funding look like, how are we going to pivot, and what those costs are going to be and things like that. So just very busy in that sense, but it's a good busy.
How is the dog? Did it get groomed?
Oh yeah, Reese looks so good. Oh my gosh, I forgot. Yeah, we had to cancel last week because it took them so long to get him groomed. I'm sorry, that was totally my fault. We got him in a bit too late, and What do I want here? I want this. Might as well move over to the math, the math frame. Yeah, it took them like I think two hours, and the groomer's like an hour away from our house. So I'm like, there's no way I'm gonna be able to get back on time to be able to do the Riemann manifolds discussion. So thank you for allowing me to push that to today. But yeah, he's a very very pretty and handsome boy right now. Until he rolls around in the mud.
That's a good boy.
All right, so welcome in, everyone. My name is Penn Center. We are joined here with Sasha, aka the Color Cone, and Slim, Academy of Useless Ideas. We'll give some shout-outs along the way here. But yeah, we're going to turn over the floor to the boys. And what Don does is... Wait, did Don change his name?
Salute. Happy to show attend.
Yeah,
he
that's
changed
Don
it.
Factorial.
He's now
The
Don
OG
Factorial, that's right.
algorithmist.
Okay.
Some
We'll get some
past
shout-outs for you guys along the way.
derive the future.
But otherwise, we're going to give
Ready
you
to
the floor
crunch your
and let's start
electrostatics?
talking
Coulomb kicks
manifolds
kid.
again.
I like the shout out to percentage target user percentage.
That's my background code. Target user is my variable, if you couldn't tell.
All right. So last time
There.
we did give the definition of a Riemann surface, and we also probably gave one of the most important example of a Riemann surface, which was CP1.
Maybe Penn Center can recall the definition for us of the Riemann surface.
Yeah, so I'm actually that's a good point. We should review this because it's been a couple weeks. So I remember something about an atlas, which felt important. So there was like a collection of maps of subsets or something like that, and that was the atlas.
Charts.
Am I going crazy, or does that seem familiar?
Collection of charts.
Charts, right? Okay. And just remind me, like, what the chart or the charts, the open sets to open sets.
Yeah, so they are from open set of your topological space to like some open set in the complex plane.
In the complex plane, okay, and then the collection of those is the atlas.
Yeah, I mean there's a
maximal
little
collection.
condition that you need to check that. So whenever you have two charts, you can look at the transition function, and what we ask is that those transition function have to be holomorphic. That was one of the requirements.
Poison Mouse says Mercator, and it is related, right? Because that's why it's named an atlas and a chart. Like the Earth in itself is a sphere, but if you look at an atlas or a map, what you do, the map is usually like in a paper on a screen. So the map is actually on the plane, and then basically what you need to do is to partition the Earth in segments. And that's precisely the same idea as a chart and an atlas in this scenario, right? The only thing that you need to be sure is what Sasha is saying, that if you're, like, for example, if you are using a part of the chart, let's say that the chart is, or that your atlas is for the Earth, right? And let's say that the atlas has two charts only, like one that has, for example, I don't know, half of the hemisphere, and the other one has the other half, right? And then at some point you may need, for example, if you want to plan a trip from Toronto to Santiago de Chile on the other side, right? At some point, maybe you're going using one chart, and at some point you may need to switch to the other chart. And basically that's the condition that you ask, that when you switch charts, everything glues nicely and makes sense. Is that a good explanation, Sasha? Or?
Yeah, I like that.
So-
that makes a lot of sense. I'm wondering is it worthwhile for us to just quickly jot down that definition so we have a foundation for today?
Yeah, maybe we can just give an example of like an atlas for CP1. So
That's the same, like, but that's not just the whole definition, right? Like, so I think it's worth to just say the definition of a Riemann surface, and then maybe the example, right? Because the atlas is just one part, right?
yeah, I mean the
Yes,
other is
yeah.
just like some kind of topological condition that you need to make sure that the space is not too weird. But those are somewhat Some of them are a little bit more like sanity for the topological space. So we need a Hausdorff condition.
So, okay,
We
so
need-
the definition of just so I'm sure that I understand. So the definition of a Riemann surface is a complex manifold of dimension 1, right? That
Yes.
satisfies those extra conditions.
So Hausdorff's uncountable axioms are required for our topological condition, and the condition that we're able to cover the manifold, the topological space with a holomorphic I class. This is the condition to be a Riemann surface.
But it's the same as being a manifold, right?
Yeah, but for manifold you need a bit more. I mean, in general, for a complex manifold, you will replace the condition that your I class is, you're mapping into the complex plane. You will replace that condition to be we're mapping to Cn, and the transition function will also be holomorphic.
By holomorphic.
Yeah.
But then, I want a definition so people don't get lost. So what would be your definition then of a Riemann surface?
So okay, you have those conditions, Hausdorff's uncountable, and usually, sometimes we will require some extra condition, so connected and compact. Okay, maybe let me put some red dot here just to say that those are, as we said last time, those are like DLCs. Connected is almost always wanted, and compact is very. I mean, most of the time we want compact, but sometimes it's useful to not have compact, just because they're example of compact, non-compact Riemann surface which are useful. And then we have, so those are just like kind of topological in nature.
And do
And
we?
the second-
So by
Yes.
the way, Ben, do you remember all of what all of those mean?
I probably couldn't give you a definition, but Hausdorff is the idea that points have to be separate, right? So that
Yeah,
you're
they
going to
can
be able to
separate
find
points.
open sets around separate points. Second countable has to do with the basis, right? So we can find a basis of open sets.
That is countable for each neighbor, right? Oh, but actually for the whole thing.
Sorry, say that one more time.
So yeah, there is a countable basis.
A countable base. Oh, right, a countable basis. Yeah, is second countable, right?
Yes, second countable is a countable basis for
Countable
topological
basis.
space.
Okay.
Yeah. First countable is like on the countable on basis, but only on neighborhoods. So we have those conditions which are just topological, and the other condition which is kind of the important one, which is locally like. An open.
Perfect calculations deliver perfect results.
Oh my goodness, thank you very much for the gifted tier 1 subscription to FAM, Bexy. Oh my goodness.
And this is the condition which is so. Okay, let me give a name to our topological space. Let's call it X. Then you say that you have an atlas on X. So those are homomorphisms. So those are homomorphisms. So this guy lie inside of C. X, sorry. This guy lie inside of V. So U and V's are open set.
Yeah, so U the open set of the space, V the open set of complex plane. Okay, yeah.
Yeah.
I think I can see the picture you're trying to draw there. Yeah.
So you ask a bunch of hypotheses on those guys. So you ask, for example, that the collection of all those UI will cover X, and you also ask that whenever I have two charts, so maybe it's a bit easier if I sort of draw the usual blobs that we write, because that's how we remember the condition, which is okay. So maybe my space X look a little bit something like that. And so a charge will be like something like that. So we have the complex plane like that. So maybe U1, V1, and let's say maybe we have another chart, which I'm gonna draw as a separate complex plane, V2, and maybe the other open set will be something like that. So we have U1, which is mapped to V1 as homomorphisms. So continuous bijection, which inverse is also continuous. And the condition which makes that into a Riemann surface, which is sort of distinct from like say a topological manifold, is that on the intersection, where the two open set meets, then we get, I mean, just because all those maps are invertible. So this is phi 1, this is phi 2. I can consider a function defined on the intersection, which we call the transition map. And the condition that those charts are holomorphically compatible is that the phi1,2, which is defined just as map from some open set to C to another open set to C, is that this map is a biholomorphisms. So this concretely just means that phi1,2 is holomorphic with inverse which is also holomorphic.
Yeah, so the map has to be, in this case, phi 2 composed to phi 1 inverse, right?
Yeah. And and then you take like the restriction to be on the intersection, but yeah, that's the
like if, and because I would like to understand the difference with the standard definition of a manifold. In the standard definition of a manifold, we don't require those maps to. We just need the map phi 1 and phi 2 to be homeomorphisms, right?
So yeah, okay. If it's a topological manifold, then this condition is pretty vacuous because, well, if you have an homomorphism with those with the space which satisfy the hypothesis we have above, then phi1,2 will automatically be homomorphism. Yes.
Homomorphism, right?
But if you want to do
a smooth manifold, right?
Then that you require to be a diffeomorphism, which is basically the same thing.
Basically, the idea. Well, the way that I understand it is the idea is that when we glue, well, if you are in a manifold, well, C can be replaced by Rn or Cn. Yeah. And then the idea is that those charts are compatible in the sense that they preserve the structure that you want to preserve. In this case, the structure is holomorphisms, right?
Yeah.
But yeah, in a smooth manifold, we may want the functions to be differentiable, for example, and then we would ask for that transition map to be smooth. And in just a topological manifold, we only want it to be continuous, but then that happens automatically, so we don't care.
Yeah, there is no need for a check. Yeah.
And we also need A to be maximal, or it's convenient if we make A maximal, right?
Yeah. So. I mean, as we say, so there's this kind of little result that we didn't answers too much last time, but there is if you define an atlas, then this atlas always sits into a maximal atlas, a unique maximal atlas. But yeah, strictly speaking, you want a unique maximal atlas. You want a manifold to be given by a maximal atlas, but in practice, it's enough just to give some chart that cover your space, and this will automatically give you a unique maximal atlas.
All right. And the prototypical example is CP1, in which
Yeah. So
since you have, so CP1 is pairs of collections that you can divide always, because you want to represent lines, so you can represent basically each number represents the slope and the what is the way that you say it in English? Pen Center should know this. When you have a line, you have the rise and the to define the slope. How do you do it usually? The rise and the
Rise over the run.
Yeah, the rise and the run, right? So basically, the idea in CP1 is that C0 and C1 represent rise over the run, but you want to represent the completely vertical and the completely horizontal line. And then two numbers also represent the same. For example, if you have 2 and 1 and 4 and 2, they represent the same quote-unquote slope. So you want to identify that, and basically the only case that you don't care is the case 0, 0, because that's the only case that doesn't make sense, right?
yeah.
And then because of that, you need at least 2 charts, and then you, obviously, I think that's what you did by the end last time, right, Color?
Yeah. So projected space come with those funny homogeneous coordinate, which has the property that you will have that z0 is equal to z1. I mean, you will have those coordinates is equivalent to those coordinate. Where lambda is just some non-zero complex number, so you can rescale those coordinates don't care if you rescale them.
Yeah. So yeah, if you think on terms of a slope again, it's like you can take different rise and runs, and as far as you get the same slope, you're talking about the same line.
Yeah, and for that we had like 2 charts, which is u0, which is the chart where the first component is not 0, so z0 is not 0. But because we can rescale them, we might as well just assume they are 1.
So I guess you can think of that like as a representative of the equivalence class, right? And you pick the representative with the 1 there.
Yeah.
I mean, I'm kind of like repeating things here in the hope that helps Pen Center, but maybe I'm just being annoying.
No, this is good. This is good.
And as you say, if we sort of draw those lines into the complex, I mean into C2, which are what the projective CP1 is supposed to represent. It's supposed to represent the line CP2. Then if you have like sort of, I mean, for example, U0, what it's saying is that, okay, let's say I have a line, and let's say it's not the vertical line that passed through the origin. Let's say something like that. Let's say that this is my line. Then this line is completely because we're interesting to line that passed through the origin. This line is completely determined by its value by its value at the point 1, z, right?
So the white point is 0, 0, right?
Yeah. So yeah, the white point is the origin. Yeah. Because CP1 is supposed to parameterize the line that go through the origin, then if I just give you 1 point on the line, this should be enough to recover the entire line, right?
Yeah. So basically, every point except for the point 1, 0 and 0, 1. If you erase those 2 points, all those 2 points are in U1 and in U0 and U1. So in the example that I gave at the beginning, is like if in your atlas, you would only need to switch charts if you need to go from 0, 1 to 1, 0, right?
Yeah.
Like that would be like like to relate it to the example that I said, going to Toronto from Toronto to somewhere else, to Santiago de Chile. I think I said, I don't know. Then the only moment in which you will need to switch charts is to go from 0, 1 to 1, 0.
Yeah, and if you write those open set as the one as I've written above, then it's pretty. It's quite easy to work out what I mean. It's quite easy to write what chart we're gonna use. We're gonna use the following charts.
Equals Z.
And the same thing for the first guy. And last time we did a little computation to compute what are the transition function. And it
So
turns
I guess in general you could take any representative, right, and just say, for example, if your representative is omega or WZ, then the first one does Z over W, and the second one was W over Z, right?
the what?
Like, I mean, you're choosing the representative 1Z to define the chart,
Yeah.
but you could do it more general and say WZ, right? And then just say that the first one is Z over W and the second one is W over Z.
Yeah. I mean, you have to do it at some point when you try to work out the inverse of phi 1 and phi 0.
Yeah, that makes
Because
sense. And then the intersection in this case would be everything except 0, 1, and 1, 0, right?
yes.
Because I mean you have to define the thing on the phi 01 is in the intersection, right?
Yeah. And maybe just to sort of, I mean, we will not really use that much the picture of the sphere, but maybe it can help to at least to visualize it. I don't really care about CP1 being homomorphic in a sphere, but
because I mean, I guess, for example, when you draw a sphere, we don't draw it in 3 dimensions, right? Even though the sphere is 2-dimensional.
yeah.
In which dimension could you draw CP1?
So if you ask, okay, that's a kind of an interesting question. So it sort of depends about what you're kind of okay. So this is an abstract topological space, right? So I mean, it doesn't really sit into Rn, right, or whatever. So you need something called an embedding, okay?
Yeah.
And the problem with embedding is that you sort of you usually have to put like an extra adjective. So do you want it to be a topological embedding in the sense that you only care about this sort of, you only care about like the topology of the space, or do you want it to be a smooth embedding? So it means that you care about the topology, but you also care about the smooth structure. Or do you want to be an holomorphic embedding, which also means you also care about the complex structure as well? And if it's topological, then CP1 will embed into R3 because CP1 is the sphere, topologically speaking.
I see.
And it's the same for smooth. But for the complex case, then CP1 never embed into any CN.
Really? So because for smooth manifolds, you have the theorem that tells you that you can always embed it in 2n plus 1, right?
Yes.
Or is it 2n? What is the theorem? One of them is easy to prove and the other one is harder, right?
Yeah, this is Whitney embedding, but so any smooth manifold can be embedded into Rn, but for complex manifold, this completely
but Rn, I mean, if the smooth manifold is of dimension n, you can embed it in which dimension? I guess that's the.
I mean, something like 2n plus 1.
2n plus 1 is I think the proof is not too hard for 2n plus 1, but I think you can do it in 2n, and the proof is just harder, no?
Yeah, I mean, you usually sort of the harder space to embed is like real projective space, which is kind of the benchmark, yeah.
Right, but then there is no similar theorem for what you are saying. There is no similar theorem for when you want to respect holomorphisms, I guess. Yeah.
And there is like kind of a very easy abstraction to see why this theorem fails in the complex case is because, okay, let's think about CP1, okay? Okay.
But you know, Kaller, I don't want to derail too much because I feel that these questions are too advanced, you know?
I mean, it will be easy to answer.
Let's get back. Let's
Yeah.
get back.
I mean, I'm still trying to figure out what these open sets are.
Oh,
So like you have U not and U1 as collections of representatives.
yeah.
So these collections I see. So I understand that that these are a line. Okay. Because I can scale these up by any factor that I want. Right?
Yeah. And basically, the only line that you cannot represent using, like, for example, U0 would be this line, right? The vertical line, this one you cannot represent because it doesn't pass through the point 1z, right?
Right.
Like it's always 0 something, right?
Yeah, but we should be able to realistically make any other line by selecting some Z.
Yeah.
Okay, so that makes sense. So U naught is a collection of. It's everything except for what you've drawn in red, then, isn't it?
Yeah, exactly. Any line that go through that is not the red line can be represented as a 1z.
So, but it's open in the sense that it doesn't contain that red line, right?
Yeah, so it has like a topology, which was the topology on CP1. We described it a bit earlier, but it was so we have C2 minus the origin, and because CP1 is C2, where we have this equivalence relation that we consider that 2 points in C2 are equivalent if they differ by a multiple. So we had just a quotient map, which is just we take ZW and we map it to that, right?
Yeah, that's okay.
And the topology was that, okay, an open U in CP1 is open if and only if, okay, maybe I would call this map Q, if and only Q inverse is open in C2.
Okay.
And here you can sort of see what's going to happen with, for example, U0. So if we look at the pre-image of U0 in C2, we will basically get C2, but we will not have the vertical axis. That will be the only missing part in C2 will be the red vertical axis.
Right.
And
That's-
this
that's
is
for
an open
this
set
one.
of C2, yeah.
Yeah. Yeah, so that makes sense. And then, so now what you want to do is you want to be able to cover the rest of the space,
Yeah.
right? So here you must be selecting U1 so that you get the vertical line, right?
Yeah, so in U1
Right,
you have
so
basically the same
U1
story,
would
just
be,
that...
would be missing this, right? In which
yeah,
case, then
yeah,
you
we'll
covered
be missing the
space.
horizontal, yeah.
Okay, gotcha. Okay, that makes
Yeah.
sense. And then, so what are these phi naught and phi 1 again? So these are going to be the transition maps, you said, right?
So phi0 and phi1 are just the charts, yeah.
Are the charts. Okay, so the charts connect us between the open sets, right?
Yeah. So they are function. So they are in bijection with, so phi0 is in bijection from U0 to the complex plane.
Right. So phi 0 and phi 1 are given by just this map, and so what we actually care about is the composition.
Transition.
Right?
Yeah.
Right. Okay. And so you're saying that the inverse or the reciprocal mapping is the one that we want. That feels inherently intuitive because we're working with this crazy system, right? Because all we're doing is swapping where the one is by using the reciprocal map.
Yeah.
Okay.
That's
yeah,
exactly
okay.
what's going on.
Okay. Sorry, I just needed to talk through that to make sure had it make sense in my brain.
Yeah, and maybe just a little picture, but I will not use it that much. But it's kind of just for intuition. So CP1 is secretly it's secretly homomorphic to a sphere, and so what will be U0 if we look on the sphere? It will basically be well, I guess it sort of depends on how we choose the homomorphism. But if you use like stereographic projection, we'll get that the U0 will basically be the entire the entire sphere minus the pole north, the north pole. Sorry. And U1 will basically be the same story, except that instead of just missing the North Pole, we'll be missing the South Pole.
Right. So effectively, you've covered the sphere.
Yeah. So in the intersection, they will just be missing 2 points. If we look at like when U0 and U1 intersect, it will basically be the sphere minus the North Pole and the South Pole. Okay. So this was for CP1, and as I said, we sort of want to get back to complex analysis. So we would probably like to define the notion of holomorphic map on the Riemann surface. So let's maybe try to do that. And after that, let's see, this definition is not too bad, for example, for CP1. Okay. So let S be, well, I guess I probably want to have 2 Riemann surface, otherwise they will be a bit lonely. Be Riemann surface. And F between S1 and S2 is called holomorphic. If for all points inside of S1, there exists a chart, let's say U and phi. Okay, there exists U and phi, which is a chart of S1, and let's say there exists also one for S2, such that I have the following. So I want my P to lie inside of U, and I also want that F of U is contained inside of V. So maybe I can just draw the setup we have. So we have my first Riemann surface, which is something like that. And we have, let's say, our point P that we want to look at in the neighborhood. So let's say I have my U1, which is my open set. And this open set is mapped by my function f to some well, I call it, I guess, v, so let me call it v. And what I'm asking is that if you get mapped inside of v, so maybe I can draw u as being I don't know, some kind of thing like that. Okay, so this guy is f of u. What I ask is just that it's contained inside of v. And so I ask you, those are charts. So this means that I have this guy, which is mapped to, let's say, u primes inside of C. And I can and I have something similar for the other side. So I also have a charts. And basically, the idea is that, well, I cannot really. Basically, the idea of the definition is that, well, we don't really know what it means for a map between two topological space to be holomorphic, but because I have those kind of atlases which are defined, I can basically I know what it means for a function from C to C to be holomorphic. So I will use this. I will use that to make my definition of a holomorphic function between two between two Riemann surface. So okay, so those are charts. So let's just remember that charts allow you to go backward. And basically, we're going to do the same thing, sort of the same ideas we did for transition function. What we're going to consider is the so what we do, we can sort of define a function which go from u prime to v prime, which we're going to maybe call it f with a little tilde above. And this map will be sort of defined as I said, very similarly to the one we had earlier. So it will be sorry, this guy's supposed to be psi. So it will be psi composed with f composed with phi inverse, which is just basically saying that we are sort of traversing the those arrows this way. And the condition for the map F to be holomorphic will be when F prime is holomorphic.
And by the way, there has to be an F tilde for every. So I mean, you have a collection of F tildes. It's not just one, right?
Yeah.
For
so every
point
chart will give you a F tilde. And
every chart or every point, in theory, it should
every
be point.
chart will induce a F tilde.
Well, in practice, it will be because your definition says if for every P
Yeah.
in S1, so for every point there is an F tilde. Obviously, you reuse the same for the chart, but
Yeah. Sometimes in the definition they require F to be continuous, but this is kind of redundant. But yeah, so there's kind of this kind of funny condition that you need F to be somewhat reasonable, because you need that you're able to find some V where some open set V where the image of F of U lie inside of it, right? But V has to be small enough that it fit inside of a chart, right?
Mm-hmm.
So if F like is pretty bad, for example, I don't know, it maps like I don't know, like a very small set to like the entire space, then this F will not have this condition. But yeah, F still, as you can see with the formula above, is completely determined by the choice of chart that you taken. And usually this guy is called usually a coordinate representation of F. And so maybe this is a bit scary. So maybe we can look at one example to see that very concretely. Okay, so I have two sets of example. So okay, which set we should start with? Okay, maybe we can start with the
easy one. Start with the easy one.
Okay, but I'm not sure which one is the easiest. So okay, I guess I will write both of them, and you will tell me which one you find easier. I mean, you think it's easier. Well, I think the first one is a bit easier because it's a bit more concrete. The other one we need to do computation.
I'll have a biased representation here and say they're probably both hard.
Okay, so I want to look at the following map, which is I'll take ZW and I will map it to Z square W square. Okay, and I want to check that this map is holomorphic.
I guess the advantage here is that you only need to check. I mean, the choice of the charts is pretty obvious, right? You only have like really two charts, and then
Yeah.
they kind of map to themselves, and each one of the maps is a holomorphism because you are only squaring, right?
Yeah.
So yeah, so that one seems fairly straightforward.
So okay, but let's do it just to have like experience.
Yeah, definitely.
So first of all, we have maybe to just, because those are defined with homogeneous coordinate, and homogeneous coordinate are a bit funky. So do you guys see why this function should be well defined in the first place?
If you multiply by lambda, you get lambda square in both sides, so you can factor it out.
Yeah. Do you see it, Pan?
Well, I guess my first instinct is, I mean, this projective space doesn't include the origin, so we should be fine to square things. But I mean, I'd like to see the calculation to make sense of it.
Yeah, so basically the worry is that because those ZWs are not unique, right? Because I can scale them up by like a lambda, right?
Right.
Kyler, so you said Z instead of Z. I feel that you're not being Canadian enough.
The what?
You said Z instead of Z.
Oh, maybe.
No, you have to say Z.
Z.
Is it something that people in Quebec doesn't do? Don't you say
I don't
Z?
know.
I have no idea. I don't know.
do you say Z or Z in the West, Ben?
I think I say a mixture of both. I think. Hello,
Yeah.
Tarnished. How you doing?
Yeah, I noticed that I spell randomizer with a Z, and I heard that it's not how like British people spell it. It's more like the American way of spelling randomizer. I was like, oh damn,
Randomizer.
I got influenced by the US people.
All right.
Yeah. Okay. So
Go ahead, please.
This is sort of the worry for well defined when we define something between CP1 is that we need to make sure that this map doesn't depend on the specific choice of Z and W up to multiplication by a constant. So let's just maybe run that real quick. So let's say instead of having a ZW, I have lambda Z, lambda W. Then what I get on the right side, I get lambda Z square, lambda W square.
Yeah, basically. So I guess in general you can only do like homogeneous functions, right?
Yes. Yeah, if you don't put something which is homogeneous, you will plot something which, I mean, if an example, it's a polynomial in each of the component here, and it's not homogeneous, you will run into issue, yeah. Then I can pull out a lambda, so lambda Z square, lambda square omega. But because, okay, I should have probably specified that, but lambda is not zero. But in homogeneous coordinate, those guys are the same as Z square omega square, right? Because homogeneous coordinate doesn't if you multiply by some constant.
Yeah. Okay. So you're checking well-definedness, right? That these 2 points that are effectively the same are getting mapped to the same place.
Yeah. I mean, just like kind of a sanity check we always ask to do. Okay, and also maybe we can just sort of look at it and just see that it's true. You can also verify that U0 got mapped to U0 and U1 got mapped to U1, right? Just because if the first coordinate, for example, let's say U0, let's do the case of U0. So the case of U0 is when the first coordinate is not zero. Then okay, if the first coordinate is not zero, then obviously the first coordinate square will not be zero. So we get U0 is mapped to U0, and the same also go for U1 to U1, right?
U0 is defined as the collection of 1z's, right?
Yeah.
And yeah, you're right. If we were to square that, I think everything works out okay. Yeah. Okay. I see where you're going. Yeah, that makes sense.
That makes sense. Okay. So to check that this map is holomorphic, we just need to map to verify that. So our map, maybe I can sort of write the diagram. So the map from U0 to C. So we have F here, which is also mapped to U0, and we have C, which is our coordinate, 5 0 5 0. we just need to verify that this elf still is holomorphic, and the same goes for U1. So maybe I should write f of restraint to U0.
Right. I'm doing good, Lone. A little tired today, but it's a good week. It's a good week.
So this is phi1, this is phi1, and this is f tilde. All right. So okay, let's maybe do the computation.
So
okay,
the phi zeros are just z's, right? Like,
yeah,
the phi ones are w's.
yeah, exactly. So so phi 0, if we sort of write it in this very in this format, they will just be they will just be that,
point.
right?
Yeah.
Yeah. So in particular,
so you're
the
looking
inverse
at
of phi 0 is just we put z and we just
So are you looking at the map from z to z squared? That's what f tilde should be, right?
yeah.
Okay.
So f tilde will be, in our case, will be phi 0 composed with f composed with phi 0 inverse. So let's maybe do the computation. Okay, let's worry about the other guy later on. But as I said, the inverse of phi 0 will just, we take some z which live inside of c and we're just gonna put in the coordinate 1z, right?
Right.
And for the rest, I'll let you fill the remainder.
Okay, let's see if we can do this. So we'll get this one evaluated at 1 squared and z squared, right? Because we're squaring both coordinates. And then this one should get sent to the second coordinate, which is z squared.
Yeah. And for the other side, this is pretty similar. It's just that we do everything for the first coordinate, but yeah, we will end up with f tilde omega is just omega square.
Right. Yeah. So yeah, similar. We can say similarly over here, right? So our f tilde should omega should be omega squared. Yeah. Okay. So I'm okay with that.
Yeah. And here, so okay, here now those f tilde are just mapped from C to C, right? And we know what it means to be holomorphic. So can you assess that those maps are indeed holomorphic?
Yeah, the squaring map is definitely locally differentiable for sure.
Yeah, definitely polynomial in Z should be a holomorphic map. Otherwise,
what does the squaring? The square one does like a fan or something, doesn't it? Doesn't it like open that up? I'm trying to remember how it works. Around I think it opens up like that or something, right?
Yeah. I mean, you probably have like sort of the picture of like the square root.
Oh, maybe
function,
that's what I'm thinking of. Yeah.
Yeah.
I'll see if I can find it.
Yeah. So basically, above like every point, so basically, above pretty much any point in CP1, there will be 2 points. So. Okay, what I'm trying to say is that for almost all for almost all point in CP1, well, I guess we don't really need, I mean, okay, I guess we can do it for CP1. We would have that the preimage of the point, so the fiber will basically be 2 points, right? Except for 2 points, which are kind of special. But okay, maybe we can just think about the map from let's say G, which is C to C, which is just squaring, right? We map Z to Z square, right?
Okay.
Then
that's one we're trying to do. Holomorphic.
So if I fix C0 to be inside of C, and I'm trying to ask when is GZ equal to Z0, right? Well, this is the same thing as solving the equation Z squared minus Z0 is equal to 0, right?
Mm-hmm.
And this equation pretty much always has two solutions except for like the origin, right?
Yes.
So what you can see is that above every point of C, there's like kind of 2 points we got mapped to that point, right?
Right.
Except for the region where you sort of have an issue. And we will see that pretty much all the holomorphic map that you can think of between Riemann surfaces are always of this nature, at least locally. So this is kind of a good example. Okay, and here's the second example, which is maybe a bit easier, but we will see that it's well. I guess I want something which is a bit more complicated, but which is also interesting. Let's look at the map from CP1 to C.
So this is a new example?
Yeah.
Okay.
Yeah. So forget about the G I wrote above. Now I want. Okay, maybe I should.
Yeah, so your last point is that before you moved examples was that holomorphic maps tend to have this feature in which you map to n to 1 in almost everywhere.
Yeah, I mean, I will give I will give a more precise statement, but basically, a lot of holomorphic map will be of this nature. They will be like some Zn. They will be of this nature of f of z is equal to Zn for some n.
Okay.
At least when we work for small open set, they will look like that. Okay.
Yes.
So okay.
And I guess that
so
makes
this
sense
exercise,
because you're working with rotations in that sense, but
yeah. And okay, let's maybe look at another example. So this one might be a bit simpler because we don't. So CP1 is a Riemann surface, and the other Riemann surface is C, which is also a Riemann surface. We probably have to point that out. But you might say, well, it's a bit simpler than the other case, but I want to know all of them. Okay.
What do you mean? What do you mean by all of them?
So I want a description of all the holomorphic function from CP1 to C.
Okay. I see.
But
So this is where you're going to
moment.
answer Slim's question.
Yeah, I guess I was partially gonna answer Sim's question, and maybe I will explain why after that. Okay, so I guess Slim already saw how we do that. I think I already showed him.
Yeah.
Did I show you that how we do that, Slim?
Don't remember if you did.
Okay, so I will do this. I will do it for you then. Okay.
Yeah, I guess I'm curious to know, are there any other functions other than, taking the nth power of both of your components, right?
You will see that even that doesn't work.
Yeah.
Okay.
I think part of the function cannot be onto, right?
No,
cannot
because if they're on toe, that would mean that C is compact. Yeah.
Yeah, so it cannot be onto. Okay, so I guess constant should work. I think.
Hey, Taco.
All right.
Thanks for the work.
Yeah, so I mean, you have two components, and how do you like the projection probably works, right? Like, doesn't it? Like, if I have ZW and I send it to Z over W.
Right.
But
That's
what
how
do
you're
I
going
do?
to embed it. Yeah.
But what do I do if W is 0, right? So I have a problem there. So
Okay,
yeah, maybe
so-
projections that don't even work, right?
Yeah. So okay, let's see how we could do it.
Oh, I mean, you could probably embed one of those problems at the origin, couldn't you?
Yeah,
let's say W was 0, you just force all of those to go to the origin. Or something. I feel like you could do something silly like that.
Yeah. I mean, you will see. There's a fancy theory. Okay, so I will do sort of. I will show this fact in. I will do this exercise in two different ways. One way I will do it very hands-on. So I will just go in chart and do the computation. And the other way we're gonna use a fancy theorem to deduce it. But it's not like a fancy theorem in the sense that you. I mean, it's probably like one of the first theorem you see in complex analysis. I mean, maybe not the first one, but at least one of the main one. Okay. So to check that, if I have an holomorphic map, then it means that it can be represented into charts, right? And clearly, in this case, f of u0 must be mapped into C, right? So what I'm really left off is that I have, and so therefore I have like a map defined from u0 to C. So this is maybe f restrained to u0, and then I have a restriction map. Well, I have the chart, sorry, I0, and I have the coordinate representation. So maybe we can call it f0 tilde. And the condition for f to be holomorphic is this guy should be holomorphic as well, right? And I should also do that for the other chart, which is U1. And again, for f to be holomorphic, we need to check that both f0 and f1s are holomorphic, right? Mm-hmm. So for f to be compatible, so for f to be holomorphic, we need f0 and f1 to be holomorphic. And I mean, they also have to be compatible, right? They have to agree on the intersection, right? And agree on intersection.
I think that forces them to be constant, doesn't it?
Yeah, pretty much. So, okay, let's maybe look at the data we have. So we have those map. So now those map are mapped from C to C, okay? And now maybe we will need some complex analysis, but from complex analysis, so such map from C to C which are holomorphic are called entire function, right?
Yes.
And sort of one result you can show using a Cauchy integral formula is that entire function are written globally as power series. So we have f0, which is given by.
And then I think, Slim, you're alluding to, isn't there like a famous theorem that says if there's some, I can't remember the condition, but if you have an entire function that has a specific condition, it has to be constant, right?
Bounded.
Yes, yeah, that's right. Bounded entire functions are constant on the complex plane. Yeah.
Well, I guess it follows from what Kaler is doing, right? Because if you can globally represent it as a power series, the only power series that is bounded will be the constant one, right?
True. Yeah.
So basically, this gives us a description of what possible holomorphic function we can have. So basically, they will be given by power series, where the radius of convergence is just the entire plane, right?
Right.
So AN and BN has to converge fast enough. Okay.
Lama asks, do holomorphic maps minus constants need to be open?
Yeah, so there's a theorem that non-constant holomorphic function must be an open function as well.
Thanks, Sasha.
So yeah, I guess there's no. I mean, probably as even a third way to show that what are the holomorphic function on CP1. Okay, so as we say, you know, so those are supposed to come from a global function defined on CP1, right? So F0 and F1 cannot be unrelated, right? They have to agree on some part, right? They have to agree on intersection, right?
Yes.
And so
But isn't the intersection at 0? Is that the intersection of those two?
so the intersection is of U0 and U1 is the
Everything where Z and W are different from 0.
exactly,
Oh,
where Z
that's
and
right.
W are
Right. So
yeah, neither
so
of them are 0.
Everything except the vertical and horizontal axes, right?
Yeah.
Yes. Okay.
And if we sort of look in, so instead of looking at U0 directly on the Riemann on the CP1, what we can do is we can look on the charts and basically the transition function that we have, so phi 0, phi 1, which maps Z to 1 over Z. This transition function is defined on C star mapping to C star. And basically, what we want to do to make sure that those functions are compatible is that we want to look at F0 in, let's say, in the coordinate of W and see what we got. Okay.
Okay.
And this is just a game of, well, okay, maybe I can do it for W. Maybe that will be easier. But it's just a game of replacing the variable W by 1 over Z. So if we use a transition function, well, okay, maybe I can write it a bit more generally what we were trying to check. So for F0 and phi 1 to be compatible, on the intersection, we need what is it? Phi 0 is equal to phi 1 composed with the transition function. So in our case, if we compute F1 composed with phi 0, 1, so F1 composed with phi 0, 1 of Z, well, Z got mapped to 1 over Z, so we just get that F1 becomes, sorry, I'm missing some tilde, just become n equal to 0, Bn, and now I have the substitution, which is W is equal to 1 over Z, so I get Z to the power minus n, right?
Yep.
Just because W is equal to 1 over Z. And so, as we said, the condition for them to be the same is that they have to satisfy this condition. So we need this guy here to be equal to this guy here. Right? And what you can see from this from this formula is that this is pretty much a Laurent series, right?
Mm-hmm.
And Laurent series for a function are supposed to be unique. And so this means that all the coefficients, so we basically have two Laurent series for the same function, right?
Yeah, there's only one possibility for them to agree.
There's only one possibility, right?
Yeah.
So basically all the Bn and all the An has to be all zeros, right? Except 1, which is which one?
Yeah, except for the A naught and B naught, right? They would have to be equal.
Yeah, exactly. So this implies that A0 must be equal to B0, and for n greater or equal to 1, an is equal to bn, which is equal to 0.
Right.
So this tells us that f0 tilde is a0, and well, f1 is equal to a1 is equal to a0 as well. So this means that f is just a constant function. So yeah, as you saw, there is not many holomorphic function on CP1, which are defined globally.
There are uncountably many.
Yeah, I guess if you see it this way, there's a lot. But okay, and maybe now we can sort of think about how this result can be seen from other perspective. So I guess Yoneda Lema gave into the chat one avenue, which is
I'll be right back,
interesting
please.
also. So I guess we will wait for Pan.
It's your chance to tell people how much you have enjoyed the last videos from the Academy of Useless Ideas.
Oh yeah, I really like all of it.
Is it true that you just watch them on a loop when you are sad and they make you happy?
Yeah,
You know?
it's even worse than that. I have like an actual farms of smartphone from like 5 years ago who play the like your video in loop, and whenever I feel sad, I just go into this room and I see like 20 phones playing your video, and I feel way better now.
I'm glad that I'm helping you with your depression. Yeah.
Yeah. So Yoneda am I saying, does this work? So f of CP1 will be open and compact. So you're assuming that f is non-constant. Yeah. Okay. And yeah, so basically what you will have is that f is open, but because CP1 is compact, this means that compact must be mapped to a compact set. But this will then show that f is also a closed map. So if f is both open and so this means the image is both open and closed. So this gives us that f must be on 2, but this implies that C must be then compact, which is the contradiction.
All right, Reese and I are back.
But yeah. Okay, so okay, I guess we will do it. I guess Yoneda lemma works for Yoneda lemma idea works for in general. So maybe we can go with this way, but we can also do it with the maximal principle. But I like the way of Yoneda lemma is doing it. Okay, so maybe I can just state the result. Okay, so let's just remind this fact from complex analysis. If f of u from C to C is holomorphic, and u, and then we ask a few conditions, u is connected, and f is non-constant, then f is an open map. So f of v is open for all v. Okay. So this is usually called the open mapping theorem. And this gives you a kind of a nice, this gives you kind of a nice behavior of a holomorphic function. And the point is this theorem, so this theorem is sort of talking about open set, and open set are sort of a local data. So this theorem generalizes directly to Riemann surface. This theorem generalize. I almost want to say for free, but maybe you have to convince a little bit yourself that there is almost nothing to check, but this should all automatically follow from the case in the complex plane. This theorem for free for connected Riemann surface.
So that would be the only extra restriction we would need, right?
Yeah, if the space is not the Riemann surface is not connected, then what we can do is we can just look at f on each of its connected part, and we will get pretty much the same result.
Okay.
So when you say that it generalizes, you mean you can replace U by a Riemann surface, or can you replace both sides of the function?
Just the left side. Well, actually, you can also replace the one on the right as well.
Right.
Yeah, so you're saying like if you take an open set that's embedded in a surface, and we have that map that goes from that to the other Riemann surface with these conditions.
Yeah.
It should be an open map.
Yeah. So maybe I can just say this. So if S is connected. As I said, the connection, the hypothesis on connected can be replaced for. If you're a bit more, if you don't want the connected hypothesis, you can just ask that the function is non-constant on all the connected components. This will basically achieve the same thing.
Yeah, like I think you were saying you kind of want it to be locally connected, kind of like in that.
Locally connected follow from. This is kind of a thing you can deduce from the topological axiom that all Riemann surfaces are locally path connected. Okay, so let's say we have an holomorphic map like that, and f is non-constant, so it just means that it doesn't map everything to a point. Then f is an open map.
What is S prime?
It's just another Riemann surface.
So yes, that and I assume that one doesn't. We don't care if it's connected or not.
No, we don't. Yeah, we don't care.
Can it be not connected? Actually, I think it.
Yeah, it can be not connected.
Really, it could.
Yeah. Well, basically, what you're gonna do is you're basically gonna map. So because S is connected, right? The image of f has to lie inside of a connected component of S prime, right?
Yeah. Okay. Yeah. So yeah.
And basically, open set don't really care if you're like working over like the connected component or if you're working over the whole thing.
All right.
Okay, and so. Yeah, so usually in the work when they write the word domain, they usually mean that it's connected. At least in English, that's what I noticed, that people, when they write a domain, they usually mean like open set, which is connected.
Yeah, that's usually how I write it.
Yeah. And okay, let's see sort of the consequence of that is that if S is connected and compact, then all functions from S to C, which are holomorphic, are constant. And here's how you deduce it. So I guess we sort of check out what that was saying within when you were doing your little thing around. So let's do it by a contradiction. So assume otherwise. F is non-constant. then what you have is that f of s must be open, right? Because S itself is, in the definition of a topology, the entire space must also be an open set, right?
Right.
So these guys will be open by the open mapping theorem. And because S is compact, well, all holomorphic function has to be continuous. We have that f of s must also be compact, just by continuity. And because C is so, what was the exercise we did on compact set? So if a set is Hausdorff, then all the compact set has to be closed, right?
Yes. Yeah.
So we have that f of s is both open and close.
Right. And we only have one possibility there.
Yeah.
Well, but I mean, technically, all C is also open and closed, right?
The what? Yeah. Yeah. But this gives us two possibilities. Either this is the empty set, which is not possible.
Yeah.
Oh, I
because
guess,
S is
yeah,
not
sorry, I
empty.
guess the empty set's a possibility too.
Yeah. But C is the only like non-trivial case. So this means that F is on 2.
So
by the way-
why can we disregard the empty set? Just because S, like we're just assuming that there's something inside of S?
Yeah. By the way, I think I forgot to mention the definition, but we want the Riemann surface to be non-empty.
Oh, okay. So yeah, okay. So it's not getting mapped to the empty set, basically.
Yeah. And by the way, I just want you to realize something is that here I didn't really use the hypothesis on C. So this part of the argument I could replace.
Or any non-compact.
I could
Riemann
replace. Well, I don't even need the non-compact net close. I could replace C by any connected Riemann surface. And basically just this sort of part of the argument just showed that if I have S between S and S prime, just as before and S prime is a connected Riemann surface, this is a non-constant holomorphic function, then F is on 2.
Okay, for that part of the argument.
Yeah.
Okay.
Yeah, the part which doesn't work in general will be the last part.
Yeah, okay.
So maybe I will just draw a line. But then we run into an issue because F of S is also compact. Does F of C, does this imply that C must be compact? Which is a contradiction. And F must be constant. Yeah, exactly. I mean, maybe here I'm a bit more pedantic, but yeah, that's the same idea that, the important point is that C is not compact. And here again, you can sort of generalize the statement to something a bit more general. So this part you can generalize to say that we can generalize the statement by replacing C by another Riemann surface where the Riemann surface on the right is not compact. And we probably need connected as well, yeah.
I assume this is, I think this should be obvious, but I have not seen it right away. Why couldn't be more Klopen sets in a Riemann surface? Like couldn't be, because it could be the case that the space has some other Klopens besides the whole thing, right? But I assume that there is a reason why that's not possible, an obvious reason why that's not possible.
Oh, because okay, for the general statement, you would need for the general statement you will need that the space on the right is connected, and this will prevent you to have a Klopen open set which are, or Klopen set which are.
Why? Well, like, I mean, I guess is it because it's a metric space or something? You know, like. I mean, right now, again, I think should be pretty obvious. I'm just not seeing it.
Yeah, this is just like true in general for connected space, right? Because.
Oh yeah. I got it. Yeah.
Yeah, because you see it.
Yeah, no, I see it. Yeah.
Okay. So this is pretty neat. And by the way, I think that this proof using the suggestion of Yoneda is a bit better than the classical proof that I was about to give using the maximal principle, because it also show you the onto properties for compact, which is kind of interesting as well. Mm-hmm. Okay. So this is sort of the fancy way of doing it, but you saw sort of the computation, and we sort of... I mean, in both cases, we had to use some level of complex analysis to be able to.
But can you hand wave the other proof that you had in mind? I mean, don't do it but kind of like to get an idea. I think each proof gives us a little bit of other perspective and other intuition.
Oh yeah, okay. I can draw it if you want.
I mean, just hand wave it. Just kind of tell us. So you said maximum principle. What's the general idea there?
Okay, so the idea is that, because CP1 is a compact, so we have this. I mean, this is basically a theorem from analysis, but I guess it's more a theorem of topology, which is if you have a compact set and you have a continuous function, then it must then the image must be compact. But in C, this means that the set must be bounded as well, right?
Yeah.
Yes.
So by the maximal, well,
I guess
this is the extreme value theorem or whatever.
Yeah, I think the idea is the same now that you mentioned it.
Yeah, and basically what you're gonna do is you say, okay, so I know that the maximum will be reached at some point, so let me look at a chart around the point where this where we reach the maximal center at that point. And then you argue that, well, the maximal is not on the boundary of a disk, like of a small disk when I look it in the chart. Well, this cannot happen, just because of the maximal principle for complex analysis. Well, if that's the case, then it means that the function must be constant, right? Because the only maximum holomorphic function is allowed to have is on the boundary of a disk, right?
Yeah, exactly.
So if it happens in the middle of the disk, then there is no it's over. The function is constant.
Right. Yeah, Yoneda Lama says that what I was asking follows from Hausdorff. Yeah, I guess, like if you have more Klopen sets, it has to be, the space would be disconnected, right? And this is,
Because if we Klopen, then the complement is open, right? So
do you need Hausdorff?
No, you don't even need Hausdorff.
Yeah, I don't think so, right? I don't think so. Yeah.
All right. Now we're going to use a fact which is very cool and it's very false if we do it with the smooth function, but it's kind of the magic of complex analysis, which is locally, maybe I will just give you the slogan and after that I will explain. Locally, every holomorphic function is of the form f to the z zn.
So Yoneda Lama says that aren't you working on a metric topology? And they don't know what Riemann manifold is, to be honest. Well, we are talking about Riemann surfaces, but I assume that a Riemann surface is also a Riemann manifold, isn't it?
Well, Riemann manifold doesn't have exactly the same meaning. Riemann manifold is a smooth manifold with the Riemannian
With a
metric.
metric, yeah.
Yeah,
the
so
metric.
they're not the same, but yeah.
They're not the same, but can you put a metric on?
You can put a
Riemannian
metric. So yeah, you can put a metric on the Riemann surface, but not all Riemannian manifolds are Riemann surface.
Oh yeah, definitely. Yeah, no. I guess what I'm asking is if a Riemann surface is a Riemann manifold.
Yeah, they are. If you put like the data, yeah.
Yeah. So maybe it's time to quickly tell Yoneda Lama what's Riemann surface again. Maybe Pen Center can tell him pretty quickly now.
Oh my gosh.
And you get bonus point if you wrap it.
Bonus points if I can remember all the conditions. So, topologically, we need Hausdorff, second countable, and the DLCs, as Sasha would say, are connected and compact. Not necessary, but nice to have. And then we need a collection of, what are they called? A collection of charts to form the atlas. And they have to agree on the boundary, if I remember correctly.
On the
intersection.
Intersection, yes, thank you. Yeah, intersections. How did I do? Did I get most of it?
Yeah, it's
the
pretty
thing
good.
is at the intersection you need the map to be holomorphic, right? Biholomorphic.
Right, they have to
So
have
you need the-
inverses, right?
What is the name of that map? The Phi 01 that you wrote?
Transition.
The transition map, yeah. The transition map needs to be biholomorphic.
Yeah.
And Yoneda Lama is not bothering, at least he's not bothering me. Maybe he's bothering or she's bothering Kaler because he gets bothered very quickly. But
What?
I mean, Yoneda Lama says, I don't want to bother you guys. I mean, at least I want to be very precise that I'm not being bothered. But yeah.
No, and
Are
it's
you
good.
being
It's good for me
bothered?
to review these things because I need to get these things in my brain too, so that I know the definitions well enough
Kaler,
to
are you-
understand the arguments.
Are you being bothered because Yoneda Lama didn't wrap their comment?
No, it's fine.
Maybe they wrap them, but it's just written like in a non-wrap way, I guess. It's all in the delivery.
Okay, so let's get back to your slogan. I'm interested about this slogan. Locally, every
Okay.
holomorphic function is of the form z to the n.
So here's a more precise statement. So let's f be a holomorphic function on U which is connected, and f is non-constant, and we're gonna assume also that I mean this is just for simplicity, but this condition is just more like how would I say aesthetic than anything else. We will have that f0 is mapped to 0. If that's not the case, then you can just do a bunch of translation to make sure it is. Then what I claim is that there exists some V inside of U open, and a biholomorphism from V to V primes, where V prime also lie inside of the complex plane, such that from U to C, well, I guess I will write with V. So from V to C, so you have F restrained to V, and you have your biholomorphism phi, which is mapped to V primes. Then okay, if this guy is a biholomorphism, then maybe we can invert it. So in particular, we can build this function here, right? And this function here will be of the form f to the z, z to the n. Okay.
Okay.
And this is what I mean by the local. So locally, a real holomorphic map is just z to the n. And so this is kind of a cool picture because this means that whenever you have a map between two Riemann surface, you can really think of the map as being like the picture. For example, for Z squared, you had this picture of like of the square root function, right? Where you sort of have like two sheet of which are sort of connected in kind of a weird way, right?
Yeah.
Then this picture will also hold like for Z, and you will have like n sheets which are sort of connected into like sort of a branch point, and basically this result tells you that all holomorphic map are like that.
Right. In which case, the only real issues we're ever going to have are on the boundaries of the sheets, right?
Yeah, I mean, if you sort of go away from like because V is kind of a small open set. So if you go away from the small open set, it will change it a little bit, but at least when you're close to that, it looks like that. Okay, so how do we prove that? So what we do is because f is holomorphic in the neighborhood of 0, we can write it as a power series, right? Right. And in this power series, we have a0 is equal to 0 because we have the condition that 0 is mapped to 0, right?
Yep.
And because f is non-constant, we know that for some m, am is not 0, right? Because if all the coefficients were 0, then f would have to be the 0 function, right?
Right.
And let's take m to be let m be the minimum when this happens. So this means that I can factor. So basically, what I would have is I would have something like that, right?
So you're just getting rid of all of the zeros, right?
Yeah. Sorry, it's supposed to be an n.
Yeah.
And what now I can take is I can just factor out z to the m. So I end up with something like that times a power series. Well, I guess I'm gonna write z0, and maybe here help me with the reindexing. I think it should be an minus m.
No, plus m.
And plus m. Yeah. Okay. Z to the n, right?
Yep.
And the point is that this guy is an holomorphic function. Let's call it gz. And the point is that because a of m is not 0, because a of m is not 0, we have that g of 0 is not 0. Right, because this is the first term in the power series expansion, right, of g, right? And the first term in the term at index 0 is the one who controlled the value of g at 0, right?
Right. Yeah.
Just basically
You've explicitly chosen it that way. Yeah.
Yeah. So basically, what we have is that fz is equal to z to the m.
Yes.
Times gz. With this property, and g is holomorphic. Okay, and now what we do is we do as follows. Because g0 of 0 is not 0.
Okay, before you finish,
Yeah.
my guess is that now you want to prove that the g is constant, right? So
No, I
guess
will not be able to show that G is constant.
No? Okay. I was trying to figure out how you'll finish the proof there, but I guess my guess.
Yeah. So because G is constant, I can take, I can choose a local, determination of the M roof. Well,
What is a determination?
so you know in complex analysis you cannot really make sense of square root, right?
Okay. So it's like a branch.
Yeah, exactly. Yeah.
Okay.
So yeah, this is you might call this a branch, right? And basically you can take branch of any square root that you want, as long as you're not trying to take it at 0, right? You cannot like there's no like you cannot make sense of square root of 0 over the complex number ever. Well, I guess this map is mapped to 0, but you sort of run into issue because this function will no longer be holomorphic, right?
Well, yeah, it's just impossible to find the pre-image of that, right?
Yeah, but if you work for like very small neighborhoods, then it's fine. You can find like an inverse function to z to the m, as long as you're not in the neighborhood of 0.
Yeah.
So what I will do is I will use this local determination, and this required me, by the way, to shrink the domain of G to make sure that we fit inside of this. We need to shrink the domain where this is defined just to accommodate to this local determination, because if let's say our percentage U is too big, then this might this G might go over it. So up to shrinking U, we might assume that G of Z is the form Z to the M GZ is equal to omega Z to the M for some holomorphic function omega. And
Alpha. Is that an alpha or no?
that's an alpha, yes. And the way you get this alpha is just you use your local determination of, I mean, how is the other word you use? The branch.
I guess a branch cut, or you determine the branch.
Yeah, you just take a branch of
the branch that you want to use.
Yeah, and then what we're left with is the following. We're left with Fz, which is equal to Z, which is equal to Z to the M time alpha Z. Right? And because G of 0 is not 0, the same is true for alpha, right? Just because of this equality that I have here, right?
Mm-hmm.
And okay, here's how we define the new coordinate. So we pose the following coordinates. We define f of z to be okay. Maybe I should. Okay, maybe I should probably use it another word, because otherwise it's going to be confusing. Let's just call it psi. Okay. Yeah, okay, I define this way, okay.
What happened with the M?
I don't want the M, I just want to consider this part.
Okay.
I want to consider this part. Okay, and now what I claim is this function is invertible. Near 0. And what was the magic word we learned last time? to make this kind of hard problem into an easy one.
I can't remember.
We use the
Hand
inverse
waving.
we use the inverse function theorem.
Inverse
So,
function theorem.
so let's compute the derivative of this guy at 0.
Oh, right. If it has a non-vanishing derivative, it is invertible.
Yeah. So if we compute the derivative, so the first guy we're gonna have
So you'll have alpha z times
alpha 0, right?
Well, at 0, yeah, and then we have to add to that the derivative of alpha at 0 times yeah. So that's going to disappear there, but we know alpha 0 is not 0, so it has a non-zero derivative.
Exactly. So this is non-zero. Hence, up to shrinking. Well, okay. So if we use the inverse function theorem, we have that phi from v prime to v. Let's see if I use the same notation I used in the diagram that was writing at the initial. Yeah, that's it. Is a biholomorphism. And phi, which we're just going to take to be the inverse of this guy, is the one we need. So now my claim is that
Guess we found an inverse.
is that this phi here. So if so this phi here has the wanted properties. And for that, we just need to convince ourselves by doing a little computation.
So we're looking at we're looking at f tilde, right? And we're trying to
Yeah.
show that this is equivalent to z to some n, right?
Yeah.
When we evaluate it at z. So we
Yeah.
found the inverse of phi, which is phi is what we want.
So okay, let's maybe just double check to make sure that I didn't do a mistake, because it's possible. So okay, so because phi is well, okay, maybe I will not write this for now, but because we know that phi is a biholomorphism, right?
Right.
Then of course I can define f tilde just by composition, right? I can.
Yes. Yeah. So that was my intuition. Was does looking at the composition help?
Yeah, I can define f tilde to just be f composed with tilde inverse, right?
Yes. Yeah.
You missed a tilde.
Right here.
Oh yeah.
Yeah.
But because phi is a bijection, this means that to make sure that phi has the wanted property, I just need to well, okay. Basically, if you have like another pretender, let's call it let's call it f tilde prime, something like that, which also make this diagram commute. That means that if you compose, okay, so if you have another, let's say,
Wait, are you showing uniqueness now?
yeah, but I mean, yeah, I guess I don't really, yeah, I guess I want uniqueness, but
I thought we were just trying to show existence.
Yeah, I mean, okay, it depends. I mean, it's not really unique because those sort of coordinate I can sort of replace them by a lot of stuff.
Right. Right.
But what I want to say is that if you fix f and you fix phi, then this elf still is unique.
Okay.
And the reason why is because phi is invertible, right? It's a bijection, right? Like another way to say is that I'm able to write the formula for f tilde just in terms of f and phi. So
Yeah, but okay. So I mean that part is clear, but don't you need to prove that f tilde is z to the n?
yeah, that's what I want to say. But what I want to argue is that if I found another function which satisfies that this diagram commutes, so this means that satisfies.
So, okay, so
it has to be the same. So what I want to do is I want to plug the thing I want, and I want to make sure it works. Yeah.
ZM in this case.
Yeah, and all that. Maybe I also okay. Do I want to do this way? Hold up.
All right, you have 7 minutes before I have to go.
Okay, I want to do it. Okay. Sorry. It satisfied that, but okay, just to be sure, we agree that if it satisfies this property that this diagram commutes, that's the same thing as saying that this diagram commutes. Right.
Inverse.
Yeah.
Yeah, psi because psi is
Yeah.
phi inverse. Okay.
Yeah, that's okay with me too.
Okay, so let's do the computation. So let's take f to be z to the zm. And let's look at f composed with phi of z. So we said that phi was
Z alpha Z?
z alpha. Oh, sorry, just z alpha. Okay, and now why am I confused? Okay. Now we just have to look at okay. Here's not supposed to be okay. We just need to look at what we did before. And one of the things we did before is we had this equality that held, right? F of z is equal to z times alpha z to the m, right?
Ah, right. Okay, so this is going to take the nth power of everything.
Yeah. So this will give us z times. Wait, I think I did it wrong. Hold up.
I feel that you would need actually kind of like the m root, but I don't know. The m root instead of zm, but I'm not sure.
Yeah, that's a good idea, right? Otherwise, we probably wouldn't have went through that process if we didn't need to use it, right?
Yeah, hold up.
Kaller, I wonder if you could write this as a series of exercises, and maybe we can start with this next week. Once we, like Pen Center and I, try to do it as exercises, because Pen Center needs to leave, and I don't think it will be wrapped nicely in 4 minutes.
Yeah, I think we should probably have something like that instead, and then we should have this is f of z.
That seems right. And
oh,
then,
maybe I did mixed up phi and psi then.
Because you're gonna you're gonna use the other diagram, right? And that's gonna come out and
Yeah, but I think I
to
mixed
the
up
end.
phi and psi. But yeah, anyway,
Yeah.
if we would start out which one is supposed to be which one, this gives us what we should have, right? We have f tilde, which is z to the m, and we have that when we compose with this guy, we get back our
Get your F to FZ, yeah.
fz. Yeah.
A long time ago, Yoneda Lama says that they remember that the complex analysis professor mentioning that this is one way to deal with multivariate functions. And I think you mentioned that motivation on the first talk about this, right?
The multi-valued functions, yeah. Yeah, and then one of the ones you look at like right away is the complex exponential, right? And how the logarithm has to find a specific branch to work on.
Yeah.
Right.
All right, so
All right,
I'm going to
this
be
was
winding
fun.
down here, my friends. I'm just going to head over to my ending screen, but if there's any kind of final thoughts, we can...
So next time we're gonna talk about something which is gonna make the algebraic topologists and people doing differential topology very jealous of us. We're gonna define we're gonna define the degree of a map, which is usually very painful to do in topology, but we will do it painlessly in our case because we're working with holomorphic function.
Nice.
So basically, the idea is that I guess we're reading. Okay. But anyway, have a good one, everyone.
Yeah, I'm sorry
Thank
that I
you,
have to run
Sasha.
here, guys.
Thank you, Kader, again. Have a good one, folks.
Good one.
And thank you so much.
so-
It was pretty fun.
Let's definitely we'll do a little recap when we get together next, and if there are some things for us to look at in the interim, I'm happy to do that in a call with one of you guys or with both of you guys before next Wednesday too.
Great.
Awesome.
All right.
So we're gonna rate into N-Simplex. Looks like N-Simplex is playing some exponential idle. So good night all, and we'll. When am I on next? I'll be back on Saturday. I'll be streaming some Zelda on Saturday, and then we'll have the competition with Zach. I think next Tuesday on the 16th.
Zeta sleep time player.
Oh.
Integrate some Z's. Differentiate the
Yeah, so
noise
until
tomorrow.
then, take care, guys,
Reset
and
your
thank you, Slim.
vectors.
Thank you,
Then we're
Sasha,
back to
for
the
coming
problems
and
at dawn.
hanging out today.
Good
Much
night
appreciated.
from Shibuya's Zeta GM.
Have a good one, folks. Bye-bye.
Bye.
All right. See ya.